Okay, so I will start with a topic which is called quantum mechanics, and the importance of this is that this is I wanted to make it general for all students, but especially with an emphasis that during your fifth semester you will be encountering quantum mechanics, and that becomes very uh, disturbing and very what should I say, very problematic for all of you to score marks and to understand it. So I just wanted to make it very lucid, very basic, and depending on your interest, I will continue to go to the depth. But for today's class, I will be delivering only on the birth of quantum mechanics, why quantum mechanics is necessary, and why it has taken the most important part of our daily life. So let us start with the topic called quantum mechanics. Now, according to Niels Bohr, who had been called one of the pioneers of quantum mechanics, he said that if you are not astonished by the results of quantum mechanics, you have not understood it. That means it says that the results of quantum mechanics are very astonishing. And if you are not astonished by the results of quantum mechanics, because this is not generally observed or generally encountered in daily life, that these observations are counterintuitive. And if you think and if you see that, yes, this is very counterintuitive, very astonishing, then I think, according to Niels Bohr, that you have understood quantum mechanics. Okay. Now, forget about quantum mechanics. Now, let us watch a cricket match. Okay. Okay. So, from the previous slide, what you have seen that we have witnessed a cricket match where KL Rahul threw the ball to the stump and the batsman got run out. Okay, it was during, let us say, T20 World Cup 2022 against Bangladesh. Now, let me connect this to quantum mechanics. Now, if we just think that, let us replace this cricket ball with, now let us assume the ball to be an electron, and let's see what happens next. Okay, this is another game. Let us say this is a game where the ball has been replaced by an electron. Now let's watch it. Okay, so what do you see? That if we replace the cricket ball by an electron, it can move anywhere. So it implies that if you have an object with a big mass, big size, then you can precisely throw the ball to a particular direction. That means it has a particular trajectory. But if you have an electron and if you throw in a particular direction, you are never sure that it will reach in the destination. It will end up in moving everywhere. So this is the difference between classical mechanics and quantum mechanics. So if we start with classical versus quantum mechanics, if we see that classical has a fixed trajectory, that means the trajectory is very certain. Certain in the sense that the trajectory which we saw in, let us say, our cricket match, that means when KL Rahul was throwing the ball, he was very certain that he threw the ball very accurately to the stump, and the stump was broken and the batsman got run out. So the trajectory is very certain. That means this certainty is only applicable, that means the objects that we can see. We can see means the object should be large in size, have a big mass, and that's why these are what should I say, daily objects or day-to-day life observations. So daily objects or macroscopic objects, that means we do not need any microscope to see them. They are very easily visible through our naked eyes. We can see that objects that you can see, they follow classical mechanics, and we should uh, consider that this classical mechanics is uh, is bread and butter of Newton, and we should also recognize the work of Newton because he actually uh, devised most of the laws of physics that the world or the universe is governing. Okay. Now, if we see the difference between classical versus quantum, so in quantum mechanics, what you see, sorry, just a minute. So in quantum mechanics, what you see that there is no fixed trajectory. That means trajectory is not well defined, and the trajectory, since it is not well defined, the trajectory is probabilistic. That means it can go to wicketkeeper, it can go outside the stadium. Everywhere there is a probability. Somewhere the probability may be higher, somewhere the probability may be lower, but the probability is everywhere not equal to zero. So it has many probabilities. So this implies that it can be anywhere at any time at anywhere at the same time. That means it implies that that the particle that we are discussing can be found anywhere at any time. So this indicates that this is an astonishing result. In the sense that you can imagine that you are sitting in your room, and at the same time, can you imagine yourself to be sitting in the classroom at the same time? But quantum mechanics predicts that if you are a microscopic object, if you are really a microscopic object, your position is not certain. You are probabilistic. That means you can be at your home or you can be at your classroom at the same time. So this is astonishing results, and this is what is called quantum mechanics. So let us welcome all of you to this virtual world of quantum mechanics. Now let us say why quantum mechanics? Because we have all the laws of physics, all the laws that govern the universe, and then the solar system, everything that moves, everything that you can see, that you can touch, that you can feel, everything is governed by classical mechanics or Newtonian mechanics. Then why we need quantum mechanics? The problem started with a big phenomenon called black body radiation. Now, imagine this is a hollow object, and I have prepared a small hole here. Okay, so that I will allow some radiations to enter. Okay, so if I allow some radiations to enter, and then the radiation will be trapped inside because there is a big small hole, so these radiations will go here, strike here, and there's a less possibility that it will come out. Okay, so this is the radiation will go by Brownian motions, or let us say reflections from here and there, but it will try not to come out because the size of the pore is very small. Okay, now if we start hitting this, what will happen? The radiation will get, these particles will get high kinetic energy, and it will move faster. As a result, as a result, these particles will move faster, and accordingly they will try to come out more easily from the hole. So the radiation will try to come out, but the probability of this, that means if I allow, let us say, 100 photon to enter, it will allow only, let us say, one photon. So what does it mean? It means that it has trapped 99% of all the radiations. So this is a phenomenon called black body radiation. Now, this black body radiation, if I put a curve like this for black body radiation, and if you see in the y-axis, you will see energy distribution. In the x-axis, you will see wavelength. Okay. Now, if you see, if I increase the temperature, the maximum of the wavelength goes, maximum of the car goes towards lower wavelength or smaller wavelength. Now we know that wavelength is inversely proportional to energy. So a smaller wavelength means bigger energy. So increasing temperature increases the energy of the particle and or energy of the photon. So this is an experimental observation. Okay. Now this has become a problem for 19th century physicists. They wanted to describe this experimental curve using classical mechanics. The first one is Rayleigh, Lord Rayleigh, who started using classical mechanics. So what he thought? He thought that electromagnetic field as a collection of oscillators of all possible frequencies. That means the electromagnetic radiation that is coming out will consist of oscillators of all possible frequencies, from low to medium to high. All possible frequencies are excited when you hit them. Okay, so this was his idea using classical mechanics. So using this idea, he derived an equation like this. So just don't bother about this equation, but see the utility of this equation. So this is energy density. This is the density of electromagnetic radiation, and it is d lambda. Lambda is the wavelength. So if we make a derivative, and the rho is given by this. Okay, just don't try to remember this equation, but try to see the significance of this equation. Now, if we plot this equation, you see that this is the experimental curve. This is the experimental curve, and this is the curve obtained by Rayleigh and Jeans. So actually, Jeans helped him to derive the equation, but his help was not very big. Minor help from Jeans, but the whole thing was derived by Rayleigh. And using this Rayleigh-Jeans law, if we plot this Rayleigh-Jeans law, you see that at higher wavelength, the match is almost good. It is almost going like experimental. But see, experimental has a maximum, but here there is no maximum. That means at higher wavelength, it is a good match, but lower wavelength, or it is not going through any kind of maximum. So what this equation actually means? The equation actually predicts that very short wavelength like X-ray, gamma ray are strongly excited even at room temperature. That means if the temperature is very low, since he considered that all possible frequencies are excited. So what he did, he actually, according to his equation, he said that X-ray, gamma ray, which are very high in uh, energy or very short in wavelength, they are all excited at room temperature. So this will lead to a ultraviolet catastrophe. That means even if the temperature of the universe or the world cools down, this X-ray and gamma ray will come to the surface of Earth. So this is not actually happening. And this is very bizarre. This is very unlogical thing is that a cool object, sorry, a cool object should radiate in ultraviolet and visible region. So it implies that there should be no darkness. There should be no night, only sunny days will only be there. Okay, so this is not what we see regularly or what we observe generally. So this law actually fails to explain this particular black body radiation curve. But what he applied? He applied classical mechanics. So that means we should not bother about only classical mechanics. We need a new mechanics that will help us in solving this issue. Then Max Planck came in 1900, exactly 1900, he used thermodynamics. So those most of you are from chemistry, so you should remember that thermodynamics is the basic of sciences all sciences. If you say mathematics, forget about mathematics because mathematics may be the forefather of all sciences. But if you say biology, botany, zoology, chemistry, physics, whatever science you say, thermodynamics is the father of all. So he applied thermodynamics, and his postulate was that he said that each electromagnetic oscillator is limited to discrete values and cannot be varied arbitrarily. That means all oscillators are not excited. All oscillators will have discrete values and cannot be varied arbitrarily. That means we cannot take any other value, any values than that has been allowed. That means all oscillators or individual oscillators will have a particular value. We cannot vary this value. So the limitation of energies to discrete values is called quantization of energy. So this leads to a term called quantization, and that's why his name is quantum mechanics. So that means the oscillators will have limited energies or discrete energy values, and hence it is called quantization of energy. And he said that the energy of individual oscillator should be equal to E equals to nh nu, where n can be 0, 1, 2. This n is called the quantum number. If your n quantum number is 0, you will have 0 energy. If your quantum number is 1, you have the energy h nu. You have, when your quantum number is 2, you have twice h nu. But quantum number n equal to 1.3, that means E will be equal to 1.3 h nu is not allowed. So the discrete values from 0, 1, 2, 3, 4, the whole integers are allowed. Okay, so this is what is called quantization of energy. So when he used that particular thermodynamical view, what he derived? He derived the almost similar equation, but slight modification, where he wrote like, just rubbing it, he wrote like, uh, if you see the previous equation, let us say, if you see this equation says that it is inversely proportional lambda to the power 4. And if you see now the equation, it is 8 by hc by lambda to the power 5 e to the power hc by lambda kt minus 1. So if we apply this equation, what he got? He got almost a very interesting curve like this. So I have highlighted like the Planck's curve, and this is the experimental curve. Now it is a good match at higher wavelength and good match at lower wavelength, and it has a maximum. So it is almost representing the experimental black body radiation curve. But if you look at this equation, there is a value called h, or if you see this h, we know this is Planck's constant. But remember, and it is interesting that Planck's never knew this value. He thought that it should be a constant. He never knew this value. But when he plotted this value by putting h equal to 1 or h equal to some value, just a value, then he got almost good match. But still there is a big difference between experimental and the Planck's curve. So he then started changing the value of h, and when he found that if I put the value of h equal to 6.626 into 10 to the power minus 34 joule into second, we Planck actually got a great match between the experimental and the Planck's curve. So that's why he proposed that the value of the h should be 6.626 into 10 to the power minus 34 joule into second. And that's how he actually then come up with the Planck's constant. But his initial idea of h was an arbitrary value. There was no particular value of h. He thought that h is a constant. He then started putting h different values, and when he put this value, he got a great match. So that means this value is due to the great matching between experimental and Planck. And that's why he said it to be a Planck's constant. Now, going to quantum mechanics more. So that has started, Planck's theory has started that black body radiation can be explained using quantization of energy. Now, if we think about, let us say, a particle means which has a mass, which occupies a space, although very small, but still it has particle character. Now, remember, particle character is nothing, is something which will have a momentum because it will have a mass and it will have a velocity. So particle character will have a momentum. Now, de Broglie, or let us say, I'll come back to de Broglie later. So wave character of particles was first experimentally determined by Davison and German in 1925 when they started sending electron beam to the nickel crystal, and they got diffraction patterns, like some were brighter, some were weaker, some were brighter, some were lighter. So they got a diffraction pattern, and they were actually very lucky in the sense that they could they did not know that temperature will have a different effect. So if you increase the temperature of the nickel crystal phase will become amorphous, and this is actually crystalline at lower temperature. So crystal will have different phase. So different phases or different Miller indices, they will diffract in different ways. This is constructive interference, this is destructive interference, constructive. So this only appears if we have crystalline phases. But when it becomes amorphous at higher temperature, then everything will be lost. So they were lucky that they could do this experiment, and these diffracted electrons is a characteristic of wave. So the wave character of electron is now established. Okay. Now coming back to the photoelectric effect, which is due to the particle nature of electron. That means electron, in the previous slide, we have said that electrons have wave character. Now we are saying a particle character. Okay. Now, if we see, this is photoelectric effect. Suppose this is the metal surface, and suppose suppose you are providing some radiation to the surface, and if your radiation, that means your radiation is h nu. If you are providing a small amount of it, a small lower frequency of it, radiation, that means if your nu is smaller, your energy will be smaller, and that energy is not sufficient to remove the electron. That means, suppose this is the energy level after which the electron will be ejected, but you have provided a smaller, lower amount of energy. That means the electron will not be ejected. But if you now provide a higher amount of energy, now the electrons start ejecting. So this difference, this amount is called work function, that you know from your last semester or last courses, that this is called a work function. Work function is defined as the minimum amount of energy needed to eject out the electron. That means if you provide energy greater than the wave work function, then only the electron will go out. So this is what is called photoelectric effect. This photoelectric effect has been observed in three different observations were made, and this is due to the great Einstein, who observed this effect. And see, the first observation is as no electrons are ejected regardless of the intensity of radiation unless its frequency exceeds a threshold value characteristics of the metal. So this is the threshold value. So a threshold, if we apply radiation less than the threshold value, the electrons will not eject. Okay. So second is the kinetic energy of the ejected electron increases linearly with the frequency of the radiation, but is independent of the intensity of the radiation. But now look at there are two important parameters like frequency and intensity. So I have made them simpler. Intensity is nothing but number of photons. Frequency is nothing but energy of photons. So if we put more photons, does not matter. It will not affect anything. But if we increase frequency, that means we are increasing energy, that will reject electrons. So that's why the third observation, if you see, even at low intensities, means low number of or lower number of photons, electrons are ejected immediately if the frequency is above the threshold. That means if the frequency or the energy is higher than the threshold. So it implies that the frequency is most important rather than the number of photons. So this reflects the particle nature of electron. Okay. Now, de Broglie came and he wanted to couple this together, the wave character of electron and particle character of electron. So de Broglie is one of the pioneering figures of quantum mechanics who said that a wave has also particle character and vice versa. That means if we have a particle, it will also have a wave. If we have a wave, it will also have particle character. Okay. So he said by simplifying an equation like this, lambda equals h by mv. So if we apply lambda equal to h by mv, where your lambda dictates wave character and your mv, as I said earlier, that particle character is given by momentum. So if your mv is higher, your wave character is lower. If your mv is lower, your wave character is higher. Now imagine a situation that when you are sitting in a classroom and your teacher has never entered into the classroom and you are shouting here and there because teacher has not come. So what will happen? Your velocity of the mind, because your mass will remain same, you cannot change your mass within a minute. So your velocity of the mind will be very high because teacher has not encountered. You are free to do anything. So your shouting will increase. The velocity of your mind or momentum of your mind will increase. As a result, your wave character will decrease, and hence when you were shouting, you saw that a person sitting near to you can only concentrate on the person who is sitting near to you, not the person sitting at the last benches, because your wave now has become very smaller. But the moment teacher comes, you reduce your velocity of your mind. Your mind becomes cooler. Your velocity of your mind becomes smaller. So when your velocity of mind becomes smaller, this will become smaller. Wavelength becomes larger. Now you have a big wavelength, and hence when the teacher is saying something, the first bench, last, second bench, as well as the last bench will applicable in macroscopic objects also. Okay, this is just a generalized viewpoint of what is called wave particle duality. Okay, but remember, if you want to observe the wave character, you can observe wave character. If you want to observe particle character, you can observe particle character. But remember, you cannot observe both at the same time. So one will appear sharper, one will become diffuse in one observation. Okay, we'll play a game for this. Okay, now let us say a goblet and a face. If you see this image looks like a goblet, but if you look closer, it becomes a face. Now your observation says that somebody will say, I will go with a goblet, and somebody will say, I will go with two faces. So it implies that the same picture can be interpreted in two different ways, and everyone is correct. Okay. Similarly, if we take a case of duck and a rabbit, and you can identify that a duck is facing leftward, and somebody will say a rabbit is facing rightward. So the same picture has two different ways of observation. All of them are correct. So it implies that an electron has both these characters together unless and until we measure it. Suppose when we measure it, somebody will get particle character and somebody will get wave character. But the same experiment will never give you particle character or never give you wave character. So same experiment will give only particle character or wave character, not both together. So that means electron possess both particle and wave character before it has been measured. So when you observe, starting observing using some experiment, we either end up with particle character or will end up with wave character. Okay, now let us play a game. Now we see that our observation, when you first see an object, or let us say that object that we showed in the last slide, the first impression is that okay, I will go with my vision. Whatever I saw, the answer is this. But if you start observing closely, or if you start giving some time for your observation, your vision and your interpretation will start mingling together or will start interfering with each other. Now, this can be played through a game. Let us start with the game. If you see this picture, and I will just observe this picture closely. You start observing this picture and you see now it has your interpretation of a face now has become a lady. Okay. If we club them together, it will become this. So the moment you start observing closely, your closeness or your vision and interference, vision and interpretation become mingling together, you are ending up with this. So at first you may see wave character, and when you start observing closely, you may end up with particle character. So this is what is called wave particle duality. But it is already hidden inside an electron. Electron has both these qualities, but when you want any one of the quality, you have to do one experiment, and if you want to see another quality, you have to do another experiment. Okay. Now the second one is Heisenberg's uncertainty principle. I will say that this is a position momentum case because we learned in higher secondary that it is impossible to precisely determine the position and momentum of the microscopic particle at the same time. That means if you want to measure the position of a particle and momentum at the same time, you cannot precisely determine them. Means if your position is very precise, your momentum will become blurred. So this is what is called Heisenberg's uncertainty principle, and I will call it a special case called position and momentum. But this definition is not complete. What you learned in higher secondary is okay, but this definition is not complete in quantum mechanics. The definition says that, the full definition says that this will only apply if they are measured along the same direction. That means if you are measuring position in x direction, your momentum should also be measured in x direction. Then they are bound by uncertainty. Then they cannot be determined precisely. But if you are measuring position in x direction and momentum in y direction, they can be precisely determined. Okay, so Heisenberg's principle, the complete definition is that it is impossible to precisely determine the position and momentum of the microscopic particle at the same time, comma, if they are measured along the same direction. And that's why this is the famous equation of Heisenberg, which says that uncertainty in position in x direction and the uncertainty in position in the momentum in x direction, not in y, x direction, will be always greater than equal to h by 4 pi. Now you see that everywhere Planck's constant is coming. So it should be always greater than h by 4 pi. Remember, the value of h is not equal to 0. So that means this cannot be 0. So that means it has a value. It is always greater than 0. The value is always greater than 0. That means you will always end up with a value greater than 0. That means position and momentum are cannot be determined simultaneously if they are measured along the same direction. This is Heisenberg's uncertainty principle relating position and momentum. Now, these are the leaders of quantum mechanics. So, Max Planck, who has been the pioneer of providing the thermodynamic view of blackbody radiation, which resulted in quantum mechanics, and then Werner Heisenberg, who provided the uncertainty principle. De Broglie provided the wave particle duality, and later, in if we do more classes, we'll see that Schrodinger is known to be the father of providing the modern equation of quantum mechanics. Then this is PM Dirac, who had also provided extensive work on quantum mechanics. And this fellow Uhlenbeck, although there are three persons sitting here, this is Uhlenbeck, and he is responsible for the property called spin of an electron. Okay, and this is Richard Feynman, who is known to be the father of quantum electrodynamics. So we'll discuss all these things in future. Now coming back to the postulates of quantum mechanics. So we have some postulates in the sense that these are some laws, and you cannot disobey these laws. You have to obey these laws, and then only the quantum mechanics can be understood. So you can never go against these laws. So the first law or the first postulate says that the wave function psi, because an electron has wave character, so if we have a wave character, it should have a wave function. So the wave function, now if you see the wave function, is a function of x, y, z. That means it is a x is x dimension, y dimension, z dimension. This is nothing but the position of the electron, and this is time. So position in x, y, z dimension and time. So the wave function is a function of position and time, which contains all the information of the system. That means the first postulate says that you have to know the wave function, because the wave function has all the information stored or needed for the system. This is nothing but a CPU of a computer. So CPU, you know that CPU stores all the informations. So similarly, the wave function stores all the information of the electron or the small particle. But now the second postulate says that to every physical observable property, remember, to every observable property, that means if we want to observe the property of total energy, if we want to observe the property of momentum, kinetic energy, whatever it may be for an electron, you must have an corresponding operator. I will discuss what is called operator. Okay. So you need an operator, so that when you use this operator to the wave function, because wave function is nothing but the CPU. So if you operate on the CPU, then only you will get the information that you need. Okay. So this is summarized in a figure like this. So these are the operators, like your mouse, like your keyboard. So if you, this is your desktop, let us say, this is your psi. Now these are your operators. So when you operate using these operators on psi, let us say you are using Word. So if you click on Word, the Word file will open up. Okay. So similarly, when you click on Paint, the Paint will open up. So depending on the operator where you are clicking, you are getting different properties. So this is what is called the second postulate. That means for every observable property, you should have a corresponding operator. So I will discuss what is called operator, then it will become very easy for you. So now, what is an operator? So similarly, or if you see this word operator, it means nothing but a mathematical symbol for any operation. Okay, any operation. Like you add, you add something, so you write plus, you subtract, you write minus, multiply, multiplication, division, integration, differentiation, taking square root, etc. So these are called mathematical operators. Now, interestingly, if we take same two functions and use different operators on the same two functions, you will get different values. Now take the example. Okay, I have taken 2 and 3, common everywhere. Everywhere it is common. 2 and 3. I have taken different operator like addition. When you add them together, you will get 5. When you subtract them, you will get -1. When you multiply them, you will get 6. When you divide them, you will get 0.66. Now see, depending on this different operator, although the functions are same, depending on these different operators, you are getting different values. That means for individual operator, you have a particular value. You have a particular value. Let us say this is V1, this is V2, but a single operator will not correspond to two different values. That means if you add and subtract, you will never get 5 in both the cases. So that means individual operator will provide you individual values. So this is what is called an operator. Now uh, in quantum mechanics, we have to define operator using mathematical symbols. But remember, all mathematical operators are not allowed in quantum mechanics. That means mathematically, all those operations are not used in quantum mechanics. Then, what are the operators that are used in quantum mechanics? The operators should follow two important conditions. The first important condition is linear. Linearity. Linearity means says, see, I have given a cap over A. A means operator. Operator may be any mathematical symbol. I have given an cap. Cap means this is the operator and these are the two functions. Okay. If operator A operating on A plus G will produce AF plus AG. Similarly, C is now the constant. If we operate A, CF and E, C, since C is a constant, we can take out the constant outside and operate on the function. Then if these two conditions are satisfied, we call them a linear operator. Okay. Now, let us take square root, which is a mathematical operator. We know that it's a mathematical operator. Now see if this square root is a linear operator or not. And if it is linear operator, it will be allowed in quantum mechanics. If it is not, then it will not be allowed in quantum mechanics. Let us see. Can we write like this? Square root of a plus g, will it be equal to square root of a and plus square root of g? I think it is no. The answer is no. So that means although it's a mathematical operator, but not allowed in quantum mechanics. So we will not use this as operator in quantum mechanics. Okay. And the second is that it should be Hermitian. We'll discuss in future classes more about this Hermitian operator. So it must follow this kind of relationship in the sense that integration of the wave function psi, this is the operator and this is the complex conjugate. Let us say if psi is your a plus ib, psi star should be equal to a minus ib. Okay, so this is a complex conjugate. So if psi, if A operators on psi and then psi star, and now just see the difference. The difference is that in the first case, it is psi, and in the right hand side, it becomes psi star. The orders are same. Here it was psi star, it has become now psi. If this is followed by this operator, then we'll call this Hermitian operator. For but for the present time being, you just remember that Hermitian operators needed are allowed in quantum mechanics, or operator should be Hermitian so that it always produces real eigenvalues. Real eigenvalues means real values that you can observe or measure physically. Okay, so the meaning is that we need to have real values. That's how you can measure it. If we get imaginary values, we cannot measure it. So the role of an Hermitian operator is to produce real eigenvalues. Now coming back to the third postulate. Okay, so we saw that in the first postulate, second postulate, or let us say second postulate, we saw about Hermitian operator which produces real eigenvalues. Then the third postulate says that the operator will produce only real or measurable or physically observable value only if it obeys eigenvalue equation. So this value equation is called eigenvalue equation, which is called operator A multiplied by the wave function psi will produce an eigenvalue A and psi. Remember, this eigenvalue A is called the eigenvalue. It should be a constant. It should be a constant, and this eigenvalue is nothing but the property that we are interested to measure. It may be total energy, it may be kinetic energy, it may be momentum, whatever it may be. So this is the property that we want to measure, and this property is called eigenvalue. And this, remember, the property cannot be a function of any quantity. It should be a constant, and that's why property should be constant and eigenvalue should be constant. So see, if this equation is followed, then only you will get real eigenvalues. Okay, and see, if this equation is followed, we call this eigenfunction, because this is a good function which will always produce real eigenvalues. Okay, so this equation should be followed everywhere to get real eigenvalues of your measured quantity. Now the fourth postulate. So as we have said, or as we have seen in Heisenberg's uncertainty principle, that that there is almost almost when you measure, when you want to measure position and momentum, they are not actually precisely determined. Or if we see microscopic particles, they are more probabilistic rather than precise, or rather than constant quantities. So they are more probabilistic. So that's why we have to measure them many times, and then we have to take the expectation value or the mean value. Just like you do in titration, in titration you need concordant value, because first titration may give you some error result. Second titration will give you some, let us say, if first titration, first value and second value matches, then you will say, okay, there is no error in my measurement. Similarly, in quantum mechanics, you have to measure the quantity, that is the property that we want to measure. We have to measure it for several times, and then we have to take the expectation value or the average value. And see, this is an operator. The role of an operator is to produce values or properties or eigenvalues or properties. So the property that you want to measure should be measured many times, and then the average value of this property will be given by this equation. So you have to remember this equation: integration of psi star a cap psi d tau, integration of psi star d. I'm taking it in one dimension, so I'm writing x. Okay, so this is the fourth postulate. Now the fifth one will be discussed more in detail in future classes. So till, let us say, fourth postulate, we have considered this wave function to be only a function of x, y, z. Okay, So we call it just like R, position, but not T. We have not included T till fourth postulate. In the fifth postulate, we will include T also. So this is what is called time involvement in the measurement is given by, or sometimes it is also known as time dependent Schrodinger equation. So it's given by, this is an operator. This operator is nothing called Hamiltonian operator, which provides total energy as eigenvalue. So if we operate with this, the equation becomes this. Now, if you see, we'll get up an imaginary number. So this imaginary number will be dealt in future classes, why this imaginary number comes. But you have to remember that if we have to use both position and time into the equation turns out to be this. Otherwise, the equation will be simply H psi will be equals to E psi. Okay, but now here the time dependency is coming on. Okay, so this is what is called fifth postulate. So I will end up with something called thank you, and our lab actually using quantum mechanics to see a beautiful picture. So most of you have heard about, let us say, called aromaticity, and in your classes in organic chemistry, your teachers perhaps said that when you have aromatic ring, there is a ring current going on, and this ring current creates a circular motion of current, and this current, if there is a current, we call this aromatic. Now nobody has seen the current till date, so we, as well as some others, taking the help of others also, we have developed a protocol that where you can use quantum mechanics to actually visualize how the current is moving in an aromatic ring. So I will take the example of the beautiful molecule called benzene, and you can see that this is how the ring current are moving along the molecular plane. So that means this the circular motion of this ring current creates a very shielding zone, so that the magnetic field need to penetrate will be required very high. So you have to provide high magnetic field to penetrate this field. So this is the effect of aromaticity, and this is only visualizable or only observable or only calculatable using quantum mechanics. Okay, thank you very much.